Good morning from Dhaka, Bangladesh. This is the second lecture of my lecture series, A-Level Chemistry. And I will now go to the number 8 slides, where I will show that we have been discussing in the first lecture about simplified diagram of mass spectrum. And I mentioned the points of that simplified mass spectrum. I also mentioned that mass spectrophotometer is a large and complex instrument, which you can see here now. The next slide, I had already mentioned about the relative atomic mass of neon from the mass spectrum, how we calculate it. And then I showed this slide showing the mass spectrum of germanium and mass spectrum of lead. I opened up 2 questions saying, write the isotopic formula of the heaviest and lightest isotopes of germanium and lead. And then use the percentage abundance of each isotope in the mass spectrum to calculate the relative atomic mass of germanium and lead. And then I showed this mass spectrum of a band chemicals and pointed out some problems to solve from the mass spectrum. I hope it would be, if it would be a interactive lecture, I could ask the students now whether they have solved this problem. Anyway, I am solving it now. You see, I have copied the mass spectrum of germanium, which is in the right of the slide. Here we have a peak at 70 mass number, and the 72, 73, 74, and 76. And you know, the atomic number of germanium is 32. So when we show this symbol of the lightest isotopes of germanium, we have to refer to the lowest mass number, and which is 70. And we usually also include atomic number of the germanium, and that is how the symbol of lightest one. Similarly, we go for the heaviest one. This is the mass number 76, and the 76 in the superscript of the left of symbol germanium, and 32 is the atomic number. Similarly, we go for the next slide and show you the lightest isotope of lead and heaviest isotopes of lead. It is clear that the lowest peak in lead is 204 mass number, and note that the atomic number of lead is 82, and therefore we show it like this. This is the lightest one, and this is the heaviest one, because the heaviest peak, the peak in 208 is the mass number, which is the heaviest one. Now we have to calculate the relative atomic mass of this. Remember that we have to take all the peaks, mass number, and their relative abundance. In case of relative abundance, you can get it from the y-axis, the value of y-axis, and get it. So here we take germanium. I go again back to the 12. Here we get germanium. We have given there here the relative abundance and the peak position. So 70 into 20.6, 72 into 27.4, and so on. And then we add all this and divide by 100. And that gives us relative atomic mass of germanium, which is 72.7. And similarly, we work out for the lead and get the relative atomic mass of lead, 207.2. Now we go for that problem, that banned chemicals. We had few questions here. I can explain from here it is. What is the probable related molecular mass of banned chemical of the mass spectrum? We have here is the chemical composition of the dihydrocodoone, carbon 18, hydrogen 23, oxygen 3, and nitrogen. We know the relative atomic mass of carbon is 12, exactly 12, hydrogen 1, oxygen 16, and nitrogen 3. If we add this number, that means 18 carbon, 23 hydrogen, 3 oxygen, and 1 nitrogen, we come out, the value becomes 301. So we get a peak at 301. So the question was, what is the probable relative molecular mass of banned chemicals on the mass spectrum? And we can see that in mass spectrum, the probable one is 301. Is the probable relative molecular mass consistent with that? Yes, it is consistent, because if we calculate this molecular mass of this one, we see that it is 301. So it is consistent. What is the relative mass of fragment lost from the molecule of the banned substance, leaving the fragment of relative mass 284? You see, the fragment, we said that during the process, the molecule may fragmented to other fractions. So we can see here a peak at 284. So if we subtract from here 17, then we get 284. Okay, what is the value of 70 then? We will see that if we take the hydroxyl group, we say relative atomic mass of oxygen is 16 and hydrogen is 1. So that means hydroxyl group has a relative atomic mass is 70. So 301 minus 17 gives us 284. So the lost fragment is an hydroxyl group. Then the next question is, dihydrocodoone contains a CH3O group and an OH group. What evidence does this mass spectrum provide for these two groups? We have already shown that this group has a relative mass 16 and this one has relative mass 31. If we calculate carbon 12, hydrogen 1, oxygen 16, we get this is 31. And there, if we take out 31 from 301, it comes out to be 270. So we have a peak at 270. So that is the evidence that this banned chemicals has got CH2O group and also hydroxyl group. That was the questions I kept for you, and I suppose the solution we got it now. Now we go for today's lecture, the next part, that is atomic structure continuation. We will talk about a mole. What is a mole? A mole of a substance is the molecular mass of the substance. And that is designated as M. Here it is, that is designated as M. The units of molecular mass is always gram per mole. Now, the number of atoms in a mole is a big one. It's 6.02 into 10 to the power 23 atoms. This number is called Avogadro constant. The symbol of Avogadro constant is L. So Avogadro constant applies to atoms, molecules, ions, and electrons. So 1 mole of sodium, there are 6.02 into 10 to the power 23 sodium atoms. Similarly, if we go for 1 mole of sodium chloride, we'll find that there are 6.02 into 10 to the power 23 sodium ions, as well as 6.02 into 10 to the power 23 chloride ions. We have to speak about it more carefully when we say we want to get the moles of chlorine or moles of chlorine molecules. We have to clarify it properly and then state it. So number of moles usually designated as MOL, here it is, and it is this mass of substance in gram divided by molar mass of the substance. And we get the molar mass if we calculate from atomic mass to the molar mass. That means that every atoms in a substance, their mass calculated, add it up, and then we get molar mass. As we know that we have to get the structure of atom. That means constituent inside the atom. And we call, when we arrange electron inside the atom, we call that electronic structure or electronic configuration. There you see. But there are various ways of representing it. In O-level, generally they show it like this. In this picture, I showed models of lithium, and the lithium is here, and then carbon, and then neon, and then chlorine. This is not an accurate way of representing electronic configuration. But this way helps us to understand the electrons involved in reactions. And this is the way where O-level chemistry, O-level students are being taught in this way about the electronic configuration. But when you go to A-level, we have more advanced way of representing electronic configuration. I am now going to show you those, how we have to do it. Well, if we remember Rutherford nuclear model, which is called microscopic solar system. Well, according to classical physics, if a charged particle circulate around another charged particle, then the charged particle continuously loses its energy by electromagnetic radiation. And thereby, it will spiral into the nucleus. If this is so, we should not get a stable atom, but we are always getting stable. So therefore, Rutherford nuclear model is also have limitations. You know, Niels Bohr, he did experiment, and the hydrogen spectrum, line spectrum of hydrogen atom, and he showed that electron moves in a circular orbit around the nucleus. Bohr also adopted Max Planck's idea, saying that energies are quantized. And if we take energies are quantized, then one can successfully explain the line spectrum of hydrogen atom. And this is what we know as Bohr hydrogen atom model. However, here we also have limitations. Bohr model can explain only hydrogen atom. But if we have more than one electron, and we do have many atoms, more than one electron, we could not explain the line spectrum of those atoms using Bohr model. Then we continue to develop different scientific development, and these developments are not in the syllabus of AS and A-level chemistry. However, if we want to continue electronic configuration, we should have an idea about this. So de Broglie equation, Heisenberg uncertainty principle, Schrodinger wave equation, these work, especially the work of Schrodinger, opened a new field of science, which we call quantum mechanics or wave mechanics, which deals with subatomic particles. However, and then we go to the next slide, showing, as I said, Schrodinger wave equation. If we solve Schrodinger wave equation, a series of mathematical functions, which is called wave function, one can get. Square of wave function provides information about electrons' location in allowed energy level states. Square of wave function says about the probability of finding electrons in space at certain point. And that's what we call probability density or electron density. You see, Bohr atom model introduces only one quantum number, that is n, which we call an orbit. But quantum mechanics model gives just 3 quantum number, which you get from Schrodinger wave equation, that is n, l, and ml, to describe an orbital. So please note an orbit and orbital. So an orbit that is coined by Bohr, but quantum mechanics say that is orbital. What is orbital then? The orbital, the probability of finding electrons when it is more than 95% in a space is called an orbital, and where we get electrons. So these we can explain with the quantum number. There are 3 quantum numbers, as I said, n, l, and m. The first one, n, is called principal quantum number. According to Schrodinger wave equation solution, principal quantum number have only allowed value, that is positive integral values. It could be 1, 2, 3, and so on. And that these numbers represent shells. If n value is 1, then we call it first shell, n value is 2, second shell, and so on. But then again, each shell has got subshell, and that we designate by azimuthal quantum number, which is L. What is L then? The allowed values of L is equal to from 0 to n minus 1. N is principal quantum number, as I said. So if n is equal to 1, there is only one allowed value for L, which is 0. So we have only one subshell in n is equal to 1. Similarly, if n is equal to 2, we have 2 subshell, because allowed L value will be 0 and 1, not more than or not less than any value. This quantum number, that is azimuthal quantum number, speaks about shape of the orbital also. Okay, we go for magnetic quantum number. Magnetic quantum number, which we designated M, small letter m with subscript L. This has got allowed values when L is equal to any value, then that means minus L to 0 plus L. These quantum number can tell us about the number of orbitals as well as the orientation of orbital in space. I should say about this, which I show you in here, azimuthal quantum number values, that is L is equal to 0, 1, 2, 3, 4, etc. And this number can be notated with small s, p, d, f, g, etc. Small s means when L is equal to 0, we can denote it as small s. When L is equal to 1, small p. When L is equal to 2, small d. L is equal to 3, small f. And if M is equal to 4, then G. These are the symbol we used. As we said, Bohr atom model could not explain the line spectra of atoms having many electrons. That has been said already. Another thing Bohr atom model could not explain. The line spectrum we get is single line, according to Bohr atom model. But there is a dilemma. When you take line spectrum of other atom, we see that it is not single line, it is a paired line. And that dilemma has been solved by two Dutch physicists. The electron have an intrinsic properties called electron spin. Now the fourth quantum number is designated as m, and lowercase m, or which you call a small letter m, and then a subscript s. And it has been seen, experimentally proved, that electron has got two allowed values. One is half, plus half, and other is minus half. And a spinning charge produces magnetic field. Therefore, two oppositely charged spin produces charged magnetic fields. That can explain our splitting of spectral lines to closed space pair. Now I take an example of third shell. What are the values of 4 quantum numbers of third shell? What are the symbol of subshell of third shell? How many orbitals are there in third subshell? So n is equal to 3. So we have allowed value for L is equal to 0, 1, and 2. No other value. So we have then 3 subshell for n is equal to 3. I said when L is equal to 0, we call lowercase s, 1 lowercase p, 2 lowercase d. So the subshell will be 3s, 3p, 3d. Now, for every values of L, ml, we will have values of minus L, 0, plus L. So when L is equal to 0, we have ml value should be 0 also, because minus 0, 0 plus 0 is one thing, same thing. So we'll have only one allowed value, 0. When L is equal to 1, ml value will have 3 values, minus 1, 0, plus 1. So L is equal to 2, ml values will be 5 values, minus 2, minus 1, 0, plus 2, plus 1. So N, L, and ml values are the allowed values, and then ms have values plus half and minus half. So in 3s subshell and 3p subshell, 3d subshell, how many electron we have or how many orbitals we can have, we can calculate it and find it out. Next slide. Now, you see, I talked about it. Then when n is equal to 1, we have only one subshell, 1s. When n is equal to 2, we have 2 subshell, 2s, 2p. When n is equal to 3, we have 3 subshell, 3s, 3p, 3d. When n is equal to 4, we have 4 subshell, 4s, 4p, 4d, 4f. I didn't show that here. So increasing energy level is shown here. And this one is a model which says how to fill electrons in each orbital. And how many electrons we can fill in one orbital. That's what it is. So Another thing, this slide says the energy values, how it increases with increase of orbitals or subshells. So this is the lowest energy 1s subshell, and then 2s, and then 2p, 3s, etc. This one, when we talked all together, we call it Aufbau principle, German word Aufbau principle, which is called building up principle. How to build up electrons in different subshell. That building up principle says so. We probably finish here and continue this lecture to show you how electronic configuration is worked out. And there are few rules and conventions to write electronic configuration. Using those rules and convention, we can write down the electronic configuration of all 118 elements. We'll talk about it in next lecture. Thank you very much.